Okay, we want to perform this integral. I've written the integral down again here. We're going to integrate first with respect to rho. We're going to get 12 rho cubed over 3, which is simply rho cubed over 4 rho cubed, and that's over 1. That would be 12 rho cubed over 3. Darn it, let's stop. Here's our mass integral for the mass of the Earth in terms of the density and the radius of the Earth. Writing the integral down again, we simply proceed. First going to integrate the inner function. Now the sine phi won't have to be integrated till we get to d phi, so that could actually be factored out to here. I'm just going to leave it in. We're going to treat sine phi as a constant and integrate with respect to rho. The integral of our antiderivative of 12 rho squared is 12 times rho cubed over 3, and that's going to give us just 4 rho cubed. Integral of rho cubed is rho to the 4th over 4, so we're going to have 9 rho to the 4th over 4r. That's evaluated between 0 and r, and then we've got our sine phi, d theta, d phi. Our substitution, straightforward. When rho is 0, both of these are 0. So we're just going to get this expression evaluated for rho at the upper limit r, which is going to give us 4r cubed minus what? 9r to the 4th over 4r. Well, r to the big R to the 4th over r is r cubed, so we're going to have 9/4 times big R cubed, which we're going to be able to simplify. I believe we're going to get 7/4 R cubed. We'll do that in a minute. And then that's times then sine phi d theta d phi. Now our d theta integral, all of this is constant with respect to theta. So we're going to have the integral from 0 to pi of what? Theta evaluated between 2 pi and 0, multiplied by these terms, and 4r cubed is 16, well, 4 is 16/4 minus 9/4 does give us what I thought, 7/4 r cubed times the sine of phi, and then that's d phi. Now the integral, or the expression theta that we got by integrating just plain old d theta, evaluated between 0 and 2 pi, gives us simply 2 pi. And what we end up with then, I'm going to go ahead and multiply 2 pi by the 7/4 r cubed, all of which is then constant, can come out in front of the integral, and we get 7/2 pi times big R cubed times the integral from 0 to pi of sine phi d phi. This is equal then to 7/2 pi r cubed times antiderivative of sine phi is negative cosine phi. That's evaluated between pi and 0. And that's going to give us 7/2 pi r cubed multiplied by cosine of pi is 0, and cosine of 0 is 1. So we end up with just 7/2 pi r cubed. I find this result bothersome because the volume of the Earth is 4/3 pi r cubed, something we could have easily obtained with a integral of this nature, just by integrating the rho squared sine phi d rho d theta d phi over the same limits. We would have gotten the volume, and density is 12 minus 9 rho over r. When rho equals r, that's 12 minus 9, that's 3. Maximum density is 12, minimum is 3. Now, because of the way the Earth gets, the way the Earth contains more volume between two distances from the center, as you move away from the center, I didn't state that very well, but the way volume increases with distance from the center, we're going to be closer probably to the minimum than the maximum for our average density. Even though the density function is linear, the lower values of the density apply over greater volumes. Even at the minimum density, the mass should equal minimum density, which is 3 times 4/3 pi r cubed, which is 4 pi r cubed. Well, 4 pi r cubed is bigger than the 7/2 pi r cubed. That would be 3.5 pi r cubed that we got here when we integrated. Integrating our density with respect to the volume cannot give us a result that's less than the average density. Well, it's going to give us a result that's equal to average density times volume. Average density is more than 3, and density 3 would give us a mass greater than the mass we've just calculated, so something's amiss. However, we have illustrated the process of setting up and performing an integral. I'll come back in the next clip and see where I went wrong. I obviously did something wrong in here, but I'm having trouble identifying it.